So this is the problem that we were doing when we were looking at angular acceleration. In particular, we had this problem where there was a hub, and around that hub, a string was wrapped. And attached to the string was a mass. And there were these 6 objects, and they happened to be pool balls, all the same mass, and they were located at some distance r from the center of rotation. Okay, so there's 2 things you have to do. This is an Atwood's machine problem. So the first thing you have to do is look at the pulley, and the pulley has the tension pulling downward, or rather I should say the, let's look at the string right at the edge of the pulley, and there's a tension pulling upward, and there's mg of the weight pulling downward. Once we let go, now it starts to accelerate downward. So the sum of the forces is the tension minus mg, and that's equal to minus ma, because a is in the negative direction. Okay, we can then use that information about the tension, because notice we do now have tension. Tension is mg minus ma. Okay, then let's look at the torque that that tension exerts. The torque that that tension exerts, well, there's only really one torque, but I'll write it as the sum of the torques. The torque is simply just that tension in the string times the radius of the hub around which the string is wound. So that's the torque. What actually happens then is I alpha. And in this case, I is each of the balls times 6, so if they have a total mass of m, times the distance they are from the center of rotation, squared. Now here's the aha moment. The aha moment is that the angular acceleration of the whole thing must be equal to the acceleration of the little hub, the linear acceleration, say, of any point on the string, divided by, well, it has to be how far that string is from the center of rotation. So it has to be little r. So we can now combine all these equations. So we're going to rewrite this one, and we get the the tension, which is mg minus ma, times the little radius, is equal to m, capital M, r squared, times alpha, which is a over r. So your next step then, and I'll let you show this, is to solve for the angular, or for the linear acceleration. You can also write it in terms of alpha and solve for that. But that's just algebra. You can do that on your own.